Hello everyone, my name is Rojefari and I would like to welcome you to another video. In this video we are going to learn about Multilayer Perceptron or MLP, which is the most famous artificial neural network algorithm that is used and is known. In this video we are going to learn about how this algorithm works, and we are going to see a couple of examples to see how we would design an MLP algorithm for prediction, at the same time whether its unique behaviors and personality, and we will compare that with regression to have a better understanding of this algorithm. Alright, let's get this. Alright, after a few recap, of course we are going to talk about prediction and what it was, and we're going to start talking about the difference between regression and MLP as far as where they come in to be able to do the prediction task. And then of course we're going to learn about more MLP, with its different components, how it goes about doing the training, and then we come back to another example to see the behavior and the personality of MLP. And of course at the end we are going to wrap up the video with a summary, but before that we're going to also have another comparison between MLP and regression. Alright, so we did talk about prediction and what prediction is. And in a very simple term, prediction is an algorithmic effort to be able to find the relationship between the independent attributes with a dependent attribute or target. Our dependent attribute for prediction is a numerical one. So that's prediction. And we did see that regression goes about capturing and finding these relationships using this regression equation. In the case of linear regression, this equation is linear. And we did see that we could actually have other types of regression equation which are not linear, and it could be many different ways of coming up with this regression. We did talk about with this equation. We did talk about it's not actually a very easy task to come up with very distinct and unique regression equation that is not linear. So that's not very easy to do. I mean, it is something that's possible if you have a good mathematical understanding, and you can come up with multivariate regression equation. That might actually be a better way than other methods that we're going to learn, MLP. But the uniqueness of MLP is that you don't have to be able to sort of come up with those crazy equations. You can actually use this structure to effectively calculate and capture these relationships. So the way MLP goes about this is using a network of neurons to be able to connect these independent attributes to a dependent attribute. So what we are going to have here for each of these input layer neurons, which we'll talk about in a minute more, we're going to have one for each of these independent attributes. We're going to have one input neuron. So what we are going to have here, so let me use some abbreviation here. So I'm going to call this IA1, which is independent attribute 1, IA2, and so on and so forth, right? So we're going to have exactly that many independent attributes, right? So this is for this, all the way to, and we're going to have our dependent attribute here, right? So our dependent attribute, which is a numerical one here, I mean, in this case. So instead of having to come up with crazy looking equation that probably, for the most part, if the number of attributes gets higher, and if our mathematical understanding is not that great, it's very hard to come up with those equations. And but MLP gives us a way without us having to be the one who comes up with those equations. And it uses a networks of neurons in a specific way that are connected, and there are some working mechanism to be able to capture this relationship that are nonlinear, but using a method that you don't need a mathematical understanding, or you don't need to come up with those nonlinear regression equations. So that's a very surface level comparison between regression and MLP, or artificial neural network for prediction. So let's learn a little bit more about that. So in this example, if you remember, we had two independent attributes and one dependent attribute. This is the example that we saw when we were talking about prediction. With linear regression, with linear ones, so this is the linear one, and other nonlinear ones, we have to come up with these equations ourselves and then go about finding these coefficients. But with MLP, this is what we would get. We would design networks of neurons, and they are connected in a very specific way under MLP, that connect the independent attributes to the dependent attribute in this specific way. So here we've got two input neurons and one output neurons, and these input and output neurons are designed based on the prediction task. In this example, the prediction task has two independent attributes and one dependent attribute. Therefore, we have two input neurons and one output neurons. But what comes in between is a matter of design, right? So here we've got 6 neurons that is connecting these two layers. We could have done a different design. For example, we could have done this design. I'm just going to draw it, and you can just sort of like see how this will be drawn. And I'm going to put the video on fast forward. Alright, so like you can see here, now I have a more complex design here. Like I said, this is something that we'll learn, that how we would go about these designs. So in this slide, what I'm trying to show you is that we have some choices as far as like how we would go about designing this weird looking network for us now, but hopefully by the end of this video, you'll have a better understanding of this network. But just like what we did with regression, we could sort of like change these equations, but we do need to have an understanding of these relationships if we are capable of coming up with these nonlinear equations. But here we can create more complex and less complex networks, and that has some specific sort of like implications that we'll talk about in a minute. Alright, so let's talk about MLP. So we started with sort of comparing at the surface level with the difference between regression and MLP. But now for a while, let's just learn about MLP, and then we'll come back to the comparison when we have a better understanding of MLP. So MLP is the most famous artificial neural network algorithm, and it is used mainly for the task of prediction. Of course, it can be adjusted to also address the task of classification, which we'll talk about in one of the future videos. And basically, one thing that you want to remember about MLP is that it uses errors as a way to induce learning. The way it learns from the data, it uses errors, and it drives errors towards improvement. So the network structure that we talked about has some specific elements, and we've already started talking about that. But let's, in this slide, learn officially about them. So as we said, MLP has neurons. These black or gray circles are neurons. They could be in the input layer or the output layer, right? So we'll discuss that in a minute too. And of course we have connections, and MLP, all of the neuron previous layer is exhaustively connected to the next layer, and that's why MLP is also known as feed-forward artificial neural network. And of course we have input layer, output layer, and hidden layers. So these are different elements of MLP. And when we go about designing an MLP, two matters comes from our design of the prediction task. When we design a prediction task, we are already decided about the number of or the independent attributes and the dependent attribute. And for each independent attribute in our prediction task, we're going to have one neuron in the input layer. And for each dependent attribute, we're going to have one neuron in the output layer. And of course, for most of the prediction tasks we've learned, we're going to have one dependent attribute, therefore one output neuron. But the number of hidden layers and number of neurons in each hidden layer is a matter of design. We actually did that when we discussed here, right? So when we have one hidden layer, in this example, we had one hidden layer that had 6 neurons. In this example, we had 3 hidden layers, which we had 4 neurons, 5 neurons, and 2 neurons, right? So that's a matter of design. So let's look at an example here. Here, we are trying to predict the student performance based on their travel time, study time, free time, and go-out time. These are our independent attributes. We have 4 independent attributes, therefore 4 neurons in the input layer. We have 1 dependent attribute, therefore 1 neuron in the output layer. And we have designed our network so we have 1 hidden layer, and that hidden layer has 8 neurons. So it could have been larger, smaller, but the question is how it is that we would go about doing this. Of course, we need to know 2 things. The first thing is, like any other algorithm, we have to find this structure and tune this for a specific data set. So we have to actually do some experimentation to find the one that works best. But at the same time, we want to know these rule of thumbs. The rule of thumbs are the higher number of neurons and hidden layers you have, the more complex your algorithm is. Therefore, you're going to have higher computational costs and you're going to be more prone for overfitting, right? So you want to also know this because you don't want to overfit your training set. At the same time, you might not be able to afford so much computational cost. So by knowing these, you should be able to design your network in a good way. So here we've got 40 neurons, right? We've got 32, we've got 40 connections. We've got 32 connections here, and we've got 8 connections here. Together we have 40 connections. So now I'm going to use this as my lead-in to how we would go about actually training MLP. Since MLP is an artificial neural network which is inspired by biological brain, including human brains, we can also use the terminology of learning, MLP learning or training, it doesn't matter. So MLP start by being initialized randomly, and the initialization part is basically assigning a random number from -1 to 1 to all of the connections in the network. So we've got 40 connections here, therefore we come up with 40 random numbers between -1 and 1. We completely create this network randomly. So the way MLP learns, in the beginning we're going to have this network that the weights are randomly generated, but in the end, when we have trained them, we have updated these networks using the dataset, and this is the process of learning. So what we are going to change here in this network is all going to be the change in the weights, right? So the only difference between the non-trained initialized network and the trained networks is that the weights are going to be updated. How are we going to be updating these weights? This is exactly the question we're going to be answering now. All right, so let's start with looking at an example of how a data set, and in this case, a data object of a data set is exposed to the MLP network, right? So here, the first data objects in this data set is exposed to this network. By that we mean the values of the attributes will be introduced or will enter to the network, and based on the weights that we have on these connections, we will get an expectation from the network. And this expectation, of course, in the beginning, because we just initialize the network and the weights are randomly selected, is going to be erroneous, and the error is going to be used for the purpose of learning, as we discussed. And the way it's going to work out, especially for the backpropagation algorithm, it is going to change the weights in such way that the next time this specific data object get exposed to this network, there's going to be less error. And that's the whole idea of backpropagation. So, the way this is going to work out, is because we are going to expose the data, the network, to all of our data objects a few times, the network gets to a state that it's going to be a good quality predictor. But how many times do we have to do this? Let me start talking about epochs of learning first. So an epoch of learning is the exposure of all of the data objects in your training set to the network. So if we expose all of our data objects in the network, we have gone through one epoch of learning. So let me paraphrase my question. How many epochs of learning do we need for the network to be successful? Well, that depends, and it needs a discussion on the definition, on the criteria of stopping the learning. But normally we have some criteria for stopping, and we will discuss that in a little bit in this video. So we did learn about the epochs of learning, and now we're going to focus on to learn about this backpropagation. Backpropagation algorithm uses this formula to calculate the weight changes. It uses, of course, the error and the weights before the exposure and the after the exposure. It also has some hyperparameters that are important. Of course, these hyperparameters are going to be used to sort of like shift the way that we want the training to happen. In this video, we're not going to discuss them in further detail. Because the purpose of this video is not for us to be able to write an MLP algorithm. Our purpose is for us to have an intuitive understanding of MLP so we can apply the already stable modules. So now let's look at how the calculation would look like. So first, let us calculate the expectations of a network. Imagine we have a simpler network. And in this network, we've got these weights, right? So these are our weights. So let's calculate the expectation on this node. This is going to be like this. It's going to be 2 multiplied by negative 0.7 plus 2 multiplied by 0.4 plus 3 multiplied by 0.4 plus 4 multiplied by 0.9, right? So you can see how simple the calculation is. Basically, you multiply the number by the connection's weight. So once we do this calculation, the value we're going to get is 4.2 for this node, and for the other node, the calculation is simple. Stop the video and make sure that this is correct, just for the sake of practice. And you will see, let me wipe this out. You will see this is going to be 3.9. And then, of course, you're going to have this, and also this statement to get to 4.1, which is to tell you that the expectation of this network is 4.1. But we do know that the actual value for this specific student, so this is one student that's being exposed, is 6, right? So how do we go about changing these weights? It's very simple. When you actually see this example, the weights are changed, so the next time this student exposed to this network, we're going to have less error, right? So what do I put? Do I increase this weight or decrease it? Of course, the answer is if I want this to be closer to 6, I have to increase that weight. So we change that a little bit, and that a little bit is calculated by the momentum rate, the learning rate, and all the other hyperparameters of the MLP, which we don't want to concern ourselves with at this rate of learning. And the same goes for the rest of them. So we just answer the question. If I want the final answer to be closer to the actual answer, what change should I apply to this weight? And we do that for all of them. And the next time we do the calculation, we actually see that instead of 4.1, which we've got 4.33, which is a little bit smaller change. So by doing this change, doing this back propagation, now student 1 has been able to leave its mark on the network. And since every data objects, in this case students, are going to have their chance multiple times to leave their mark or change the network a little bit, the network is going to move towards a state that is going to be a good predictor. So the question that how we are going to be stopping the learning, it can be in multiple ways. You could be stopping it after a certain number of epochs of learning, let's say after 200 epochs of learning, or you could be stopping it, let's say by if you haven't seen significant improvement in your results after 6 epochs of learning, and so on and so forth. Again, that's another sort of hyperparameters of this algorithm, something that we will have to deal with, but we don't want to at this rate or at this video to concern ourselves with a lot in greater details. So now let us look at the performance of ANNs for us to sort of have an understanding of how it would actually look like if we were to perform some MLP. So in this example, we've done 7 experiments with MLP, and on each of on the student data, the student performance data, and we can see the performances are largely similar, but they are not the same. And the difference comes from the fact that the networks are initialized randomly. Remember, we initialize the network by assigning random weights to the connections, but we can see that even though the initializations are randomly done, but for the most part, when some of the data objects are more challenging and some of the data objects are less challenging for the MLP to classify. But we can see there is a somewhat harmonious performance among all of these. But now let's compare that with linear regression. When we compare it with linear regression, the superiority of MLP stands out here, right? But we also see that it's an interesting pattern here that in the cases that linear regression had trouble predicting, MLP doesn't have trouble predicting, and vice versa, which is interesting, and that could be a starting point for a hybrid algorithm. But that's a tangent. Let's come back to this comparison. We can see even the worst case of the MLP is doing better than the linear regression. And why is that? So the question here is why MLP is doing better, and I believe you can answer that question by just looking at this slide. Before I give out the answer, stop this video and think about it for a minute. Of course, the answer lies within the fact that while linear regression has only 5 coefficients to adjust so the relationship between the independent attributes and the dependent attributes is captured, MLP has 4 big connections, and this in itself tells you how much MLP had the potential not only to capture nonlinear relationship but also multivariate relationships between these independent attributes and dependent attributes. But let me pose another question. Between these two trained MLP and trained regression, which one is more interpretable or transparent? And the answer is obvious again. Even though with MLP we have managed to create a model that is more capable in capturing nonlinear relationship and perhaps gave us a better prediction, but it sort of loses its interpretability for a human consumer, right? Meaning for us, looking at these all weights does not have that much interpretability. Of course, these weights are finding some patterns in the data that is driving that successful prediction, but at the same time, it's not really capable of giving us any insight. On the other hand, because linear regression kept its simplicity, now we can look at these weights. They actually give us some clue about the pattern in the data. For example, we can see if the study time is higher, there is a positive value here, then it improves the performance, which is something we can understand and we can use for improving student performance. Now let's compare MLP and regression. By regression here, I mean linear regression. So MLP is more complex. Of course, it's capable of more capturing nonlinear multivariate relationship. Linear regression is simpler. Of course, only linear relationship. Linear regression can give us some insight and is more interpretable, but MLP is famous for being a black box. MLP is random and it's more computationally expensive. Linear regression, it's just a formula that you're using. Of course, if you are using nonlinear regression, there might be some training algorithm that uses some computational method, but for the most part, regression does not use a lot of computation. Linear regression specifically doesn't have much designing. Basically, you've got your independent attributes and your dependent attributes, and the equation is always the same, and that's just it. But for MLP, you can do a lot of design. You have your network, you have other hyperparameters, and all of those things can be used to improve the performance of MLP. Another things that we want to discuss, of course, we've already discussed, the fact that these need to be designed. There are a lot more things that you have to consider and tune for a successful MLP. And we're going to see those things in action. I mean, if I want to go over them right now here, they're not going to make much more sense. We will actually, once we get to start working with those, we'll actually have the chance to tune those in action when we are actually creating an MLP. Let us go over the limitations and the strength of MLP. Like we talked about, MLP is a black box. While it gives us good hit rate, but it doesn't tell us what are those patterns that is reaching this good prediction rate. It's random. It could be seen as a deficiency. Is it defendable? I mean, it's, these days, by everyone being more open towards deep learning and artificial intelligence, it's becoming more and more defendable. There is no denying that linear regression is very well respected, very well developed, and it's much easier to defend it. And of course, MLP has a high computational cost. On the strength of MLP, it's very hard to find an algorithm that beats the hit rate of the MLP. It's always, most of the time, comes on top as far as being able to capture complex relationship and have a really good success rate or accuracy rate. It has a very adjustable design. You can make it to be more complex, or it can be less complex. So it's a matter of design for MLP. It is complex. While we talked about its complexity to be a bad thing or a negative aspect because it needs more computational cost, but at the same time its complexity can help us capture more complex relationships. Of course, another thing that is very unique, especially when it comes against linear regression or regression in general, MLP is very resilient toward outliers, in contrast with regression that is very prone to outliers. In summary, in this rather long video, we talked about this multi-perceptron algorithm, which is the most famous artificial neural network algorithm. We talked about how it works in a very intuitive way, and also we saw its uniqueness, advantages, disadvantages, using a couple of examples, and at 2 different points during the video, we talked about how it's different and similar to regression. Until the next video.